I'm welcome. I'm trying to learn electrical engineering today, Ohm's law, and after we've done that, we're gonna do a bit standing yoga. And if you participate in standing yoga, then it's very honest. Ohm's law. The above example makes an assumption. It assumes that the resistance of a piece of wire has the same value whatever current is flowing in the wire. Okay, what we have was that if 1 volt is lost, I didn't realize that. The amount taken away by a resistor is 1 volt. A resistor is said to have a resistance of 1 ohm when the current of 1 ampere flows in and the potential difference of 1 volt exists across its ends. 1 ohm means that 1 volt was taken out of per ampere flown in into something. 1 volt is taken away. But a resistor with an ohm of 1 takes away 1 volt when 1 ampere is put in. No, but that assumes that the resistance of a piece of wire has the same value whatever current is flowing in the wire. So we're saying it's all the time the same resistance. In science, assumptions of this kind can't be made without some experimental evidence for their truth, and experimental evidence is stated in laws. Ohm's law states that the current flowing in a conductor is directly proportional to the potential difference across its ends, providing the physical conditions remain constant. The amount which is lost while it flows through the wire is directly always in the same difference as the amount which is put in. 1 ampere loses 1 volt, 2 ampere loses 2 volt, 3 ampere loses 3 volt. Providing the physical conditions remain constant. I think the meaning that not just the wire makes suddenly. I still don't know what it is called. Whatever. This law was first stated in 1826 by George Simon Ohm. The law is usually verified by setting up a circuit shown. Some type of circuit, I think that. By altering the value of a variable resistor, a series of different currents shown on the ammeter A. A is an ammeter, but what is an ammeter? By altering the value of the variable resistor, a series of different currents shown on the ammeter will flow through the fixed resistor R. Associated with each current is a corresponding potential difference which is shown by the voltmeter. I think we just know what I just said. 1 ampere makes 1 volt, 2 ampere makes 2 volt. These various pairs of readings can be illustrated graphically. The graph obtained by this experiment is found to be a straight line through the origin. If we double the potential difference across the resistor, the current is doubled. We're saying 1 is 1, 2 is 2, 4 is 4, 8 ampere in, 8 volt are lost. The thing is 8 ohms. The graph obtained has 1 ohm. 1 ohm takes away 1 volt. We had it in an example that previously. Then a potential difference of 200 volt exists across the ends of a piece of wire. So 200 was lost, and we had put 5 in. Then there's not 1 lost. Then we're having something that has a resistance of 40 ohm. I didn't understand it. And I didn't understand the last part. The graph obtained by this experiment is found to be a straight line through the origin. If we double the potential difference across the resistor, the current is doubled. It's called treble. If we treble the potential difference, I think I heard it 100 times, but I couldn't associate it with anything. This sort of relationship shown by a straight line graph through the origin we call direct proportionality and can be taken to show the truth of Ohm's law. We're just talking about that it is proportional, that Ohm is true. But it's a good way to explain it again. Potential difference across resistor in volts. Current in resistors in amperes. It's always a 5-time thing. We are having the potential difference is 0.55 volt. Whatever, it is always for 5 times thing, what is what we're saying. And it is interesting. That means even if you have along a cable line of whatever, if you try to transfer electricity or current from one station to another station, we cannot just say, hey, we're putting double as much ampere onto it, and we don't lose so much. We're losing always the same amount. No matter if we're putting double as much current into it, we're going to lose double as much. We cannot just do it faster, but that's really another thing. We cannot just do more into it and become more, if we're pushing more through it. That is what we're talking about. It would be an interesting idea, but it doesn't work. We cannot put the double amount of ampere onto our, it's called, onto our wire, whatever, and it will not come over. It will still lose double as much. It is possible to raise certain objects to the deduction made from this particular experiment. First, the graduations of the 2 meters used will have been put on the dials in such a way. First, the graduations of the 2 meters. I think it was the thing about that. Of the 2 meters used will have been put on the dials in such a way that the truth of Ohm's law has been assumed. So first we're assuming it. This gives rise to a situation rather like using a clock to prove that there are 60 minutes an hour. It cannot be done because the maker assumed this was the case when he made the clock. Secondly, whenever a current flows through a resistor, heat is produced and the temperature of the resistor increases. We have to assume that the temperature rise is so small, indeed we use only small currents for this reason, as to have an insignificant effect on the values obtained from the 2 meters. I cannot completely follow, but I think we're saying something about it doesn't matter if it gets warmer, and if it gets warmer we have to take care that it doesn't have an influence, so we're taking not 1000 ampere onto it or 500 comparing with these two, we're putting just a little amount of amperes onto it. And then that's the example of a clock. but the essence of it, someone cannot make a 60-minute clock without having a 60-minute clock. So what was a 60-minute clock can make a 60-minute clock? Oh yeah, okay, whatever. We have to assume that the temperature rise too small. Perhaps it is safer merely to say that such an experiment illustrates the approximate truth of Ohm's law, rather than to say it proves anything. Now it should be possible for the main problem to be made clear. The resistance of a conductor is defined as the ratio of the potential difference across its ends to the current flowing in it. That is, potential difference and volts divided by current in ampere equals resistance in ohms. I understood that part now. Now it should be possible for the main problem to be made clear. The resistance of a conductor is defined as the ratio. Okay, we're saying it again. The more we lose, the much which we have lost gives indicator about how much was put in. Because we're going to lose always so much as the resistor takes out of it. And if it was taking out 10 and we're having one with an ohm of 10 running, then it was put 1 ampere. And this value of the resistance of a particular conductor is constant, proving the temperature doesn't alter. Yes, it's always the same, but not if the temperature rises, do we say? Or maybe. Although it is true to say that when a piece of wire becomes hot, its electrical resistance increases. So if the resistance increases, it gets lower, it increases. Why ever, Stephanie? Because if it gets hotter, it expands, and now the atoms are further away, and it's harder for the electricity to jump from one block to another. Although it is true to say that when a piece of wire becomes hot, its electrical resistance increases, this increase is quite small in circuits, which we will be considering in the early part of this book. Nevertheless, a wire filament in a lamp which becomes white hot when a current flows through it Let's explain some things. No conclusion out of it, but it comes to the same kind of sense. When a current flows through, it will change its resistance considerably in so doing. Typical values for a domestic lamp would be a cold resistance of 40 ohms and a hot resistance of 450 ohms. That means that thing is way hotter, and now it has much more resistance. I don't know if it means that it needs more electricity or less. I think it takes less. Whatever. That is the explanation of the lamp thing. I haven't looked from when this book is. Maybe this book is some decades old. But that is the thing of the lamp thing. We're basically saying if a wire gets hotter, the resistance gets higher. Now, it was the electrical engineering part. If you were here for electrical engineering, you can go directly to the next part of electrical engineering. We will do an Overstay yoga. If you say participating in yoga, then it's with the hours. We've anything else. Breathe out the arms down. In the arms up. Out and down. In and up. Out on the side. In and up. Out on the other side. In and up. Inch space between the feet and out on the side. In and up. Out, sink down. Out to the other side. In and up. Out and down. In and up. Out, lean onto the knees. Breathe in. And out the head of the back of the cat. In into the middle. And out the belly of the back. The cow. In. Out the head again. In. The belly. In. Out come the front. Back up. Back at the top of the backward shoulder. Breathe in the arms up. Out up the side. In and up. Out the arms over the sides down into the chair. Breathe in, come halfway up. Come high up. Down. Breathe in, reach high. Out up to the side. In and up. Out the arms over the sides down. In halfway up. Higher up. And out and up. Breathe in, come up on the zip down. And out and sink down. Right and up. Out and down. And in and up. Out the arms on the sides, down, feet together. Breathe in with the right leg. Breathe out, stretch left leg. In and change. Out, stretch right leg. In and change. Out, stretch left leg. In and change. Out, stretch right leg. In and down the middle. Out and down. Breathe in with the right hand up to the sky. Breathe out, bend the left knee and look over the right shoulder to the right hand. In and down. Out and down. Breathe in with the left hand up. Breathe out, bend the right knee and look over the left shoulder to the left hand. Breathe in and down. Out and down. Now make a half of space between the feet, shift the weight to the heels, and breathe in and cut out. And breathe out and come up. In and down. Out and up. In and up. Out and up. Now take hold of the elbows and gently rock from side to side. Hands in and down, feet together. Breathe in, come halfway up, straight back, monkey half lift. Out and down. In, halfway up. Out and down. Breathe in. In, out. Arms on the sides up. And down. Intertwine the fingers behind the back, feet same together, tall up, shoulders back, breathe in. And out, head over to one side. Chin down to the clavicle. Hold the hands down to the shoulders. Breathe in, lift the gaze. Then head over to the other side, shoulders back, breathe in. Out, chin down to the clavicle, pull the hands down to the ground. Breathe in, lift the gaze, back into the middle. Intertwine the fingers behind the back again, bring them over to one side. Shadow the wide apart with the feet, pull up, shoulders back, breathe in. Out, head over to one side, chin down to the clavicle, pull the arm and the shoulder. Breathe in, lift the gaze. Turn the head over to the other side. Bring your hands over to the other side. Breathe in. Out, chin onto the clavicle. Pull the arm and lift the shoulders. And lift the head again and turn it back into the middle. Have the feet standing together. Breathe in, lift the arms up. Breathe out, lean back. Draw the shoulder blades together. Breathe in, lift the gaze. Breathe in, come up with the hands again. And breathe out, open the chest, draw the shoulder blades together. In and up. Intertwine the fingers and reach high. Breathe out, reach the front of the back. In and up. Intertwine the other way around. Breathe in and reach high. Breathe out, reach the front of the back. In and up. Out, lean back, long arms, the sky hugger. In and up. Out, lean back. bring it up. Roll it down the face. Lift the arms up. Bring the hands to touch and lower the hands down to heart center. That was to say, I thank you very much and until next time.